Thank you. Welcome, everybody. Today, we're going to talk a little bit about applying synchronous motors to variable speed drives. We're going to get started here in a second. Uh, as Tracy said, we have Frank Oborny here, who is going to answer questions. You can type them in, and I will get to them at kind of as they come in or at the appropriate time during the slideshow. So we'll get started now. I get a lot of questions about synchronous motors and what type of synchronous motors we can use on the drives. So we're going to talk about some basic fundamentals here. The best thing to do is make sure that we understand how a synchronous motor works. So we're going to start off here in section 1. We're going to talk about some general AC motor theory. We're then going to go into section 2, which we're going to talk about the basics of synchronous motors. In section 3, we're going to talk about a brief history of the synchronous motors, why we had them, and what applications that they were used in. In section 4, we're going to talk about 3 different types of synchronous motors, because all synchronous motors are not the same. So we have to handle each one a little bit different. In section 5, we're going to talk about operating a synchronous motor on a VFD. And section 6, we're going to have special considerations or configurations that we're going to look at some of the special types of jobs that we've done in the past. And at the end, in section 7, we're going to talk, we'll do questions and answers. Like I said, some of the questions we will answer along the way, but if there are questions that are more applicable after the presentation, then we'll do them at that time. Okay, so we're going to look first at the general AC motor theory. To understand a synchronous motor, we need to look at a few basics. We're not going to spend a lot of time on it, but there are some things that we need to make sure we understand. Okay, here we see a representation of a standard induction motor. And I'll get my pointer here. If you look, you can see the stator windings. And in the middle here, you see the squirrel cage winding that's in part of the rotor of the induction motor. Now here we have 3-phase AC. And as we apply that to the stator, we're going to get magnetic field generated. And as the waveforms change from positive to negative, it's going to switch the polarity of the magnetic fields. So what we're going to get is a rotating magnetic field going around the stator. Okay, this is just your standard induction motor theory. The squirrel cage induction, the rotor, is made up of these bars. So anytime you have a conductor, you have flux, and you have relative motion, you're going to get an induced voltage. So what happens is current's going to then flow in the squirrel cage, and you're going to set up a magnetic field on the rotor. So what happens is you have one magnetic field turning, you'll have a magnetic field here on the rotor, and the interaction of those two magnetic fields is going to produce a force in a rotational direction, which is called torque. So that's how an induction motor works. One of the things, if you remember, I said we're inducing the fields into the rotor. So these poles on the rotor are produced by induction. So if this field is turning and the rotor turns at the same speed, you're not going to get an induced field. So we have to have what's called slip, which means the field in the stator is going to rotate at one speed. The rotor is going to turn at some speed less than that, and that's called slip. Okay, now let's go on to look at the speed torque curve of that induction motor. First of all, you can calculate the speed of the magnetic field by this formula. The synchronous speed is 120 times the F, which is frequency over the number of poles, which tells me a 4-pole motor is going to, magnetic field is going to turn at 1800 RPM. However, we said we need to have slip. If you look at this graph is telling us as this torque is increased or load, you'll notice that the speed across the horizontal axis is slowing down. So what's happening is the slip increases to produce the more torque. So the heavier the load, the slower the motor will actually rotate. Okay. That slip is usually in an induction motor about 3% slip. So the magnetic field is turning at 1800. The rotor is turning at about 97% that. So that's in an induction motor. Now let's look at what happens with a synchronous motor. Okay, so this is a drawing of a synchronous motor. You'll notice we have the same type of stator windings, and we will flow current through it just like we did the induction motor. There's really no difference from an induction to a synchronous as far as in the stator windings. What is different is when you look at the rotor, you can see these wires wrapped around these poles, and they're actually, in this case, wired out to some slip rings, which they put brushes on. And what we're going to do is apply DC directly to these coils. So instead of using induction to create the poles on the rotor, we're going to directly induce DC into the coil, and we'll make a magnet that will align with the stator magnet. In this way, what happens is these poles, the north and south here, are going to lock in step with each other. That's where we get the term synchronous motor. They're in synchronism. So as we rotate our magnetic field around this stator, the rotor will stay in step with that magnetic field. So we will not have 3% slip. The rotor will actually turn at the same RPM as the stator field. Now, in this case, we're looking at a brush type motor where we'll put the DC straight into the brushes. There are motors that are called brushless, which we'll talk about a few slides later, and you can actually have permanent magnet. We will not be dealing with permanent magnets on this webinar today. Okay. Now, remember we looked at the induction motor had a speed torque curve, whereas if we increase the load, the speed would decrease. Well, here's the speed torque curve of an induction motor over here on the left. You can see it's turning at 1800 RPM at a very light load. As you load it up, it will turn at the same 1800 RPM. It will go, if you continue to load it up, eventually you come to a point in which the motor will pull out of synchronism. And when that happens, you will need to trip off line. You basically shut the motor down. It's called a pull-out trip. Okay, so that's a little bit different than how we do it on the induction motor. Okay, there is another term that we need to familiarize ourselves with, and that's called torque angle. At light loads, the north pole here on the rotor in the left picture and the south pole on the stator are locked directly in sync. As we continue to increase load, the rotor will start sliding behind slightly, and this is what's called a torque angle. So as this starts to ride behind it, it's still turning at 1800 RPM, basically synchronized, but the angle starts to increase. Where we talked about pulling out is when this North Pole over here gets far enough that this magnetic flux can't keep it locked in, and we will pull out of synchronism. Okay. Now, one characteristic of a synchronous motor is it is not self-starting. An induction motor, you put power to it, the revolving magnetic field induces the poles into the rotor, it starts to turn, and it comes up to speed. With a synchronous motor, that doesn't happen. So they had to build into the motor a special winding, which is called an amortisseur winding, which is nothing more than the same type of squirrel cage that's in the induction motor. You can see in this picture these bars here and these bars that go through the field poles make up that squirrel cage. So what you do is you apply, just like in the induction motor, you apply the stator field or stator voltage. You induce the current in here, so you are using induction to start it, and this winding starts to rotate it. Once we come up to about 97% speed is when we'll be able to transfer from the start mode into the synchronized mode. And we'll see that a little bit better as we go along here. Okay, there's another thing we need to be familiar with, and that's called a V-curve. When you buy a synchronous motor, it should come with a V-curve. And if we look at this, across the bottom here, the horizontal axis is the field current. Going up the left hand, the vertical axis, is the stator current, what we call our motor current. You'll notice there are some dotted lines going from the point here at the bottom up, and there's numerous ones. Those are power factor curves. And these V's, or looks like U's, are the load lines. How you read this is, let's say we have a motor that has a 6 amp field to it. So if you come across the bottom to 6 amps, and then you come up, let's say we load our motor to 100% current, 100% load, I mean, not current. And where those two intersect, you can see what the power factor will be, which is 0.8. And if you go across to the left, you can see it's 100% current, 1.0. Okay, so if I vary the field current, I can change the power factor. I can change different characteristics about the motor. One misconception is if I look at the motor stator current, that's an indication of how much load I have on the motor, and it's really not. You could have a very lightly loaded motor with a 100% field, and it looks like you're at full load amps when you're actually the motor load, even though it shows full load amps, would be very light, 10% or so. Okay. So in this case here, a perfect example, we've got the same curve, and instead of having 6 amps, remember we had 90% power factor, and that's at 100% current. We're on our 100% load. If I reduce my field current from 6 to 5, where it intersects 100% load is at a power factor of 0.9 leading, and I'm only getting 0.9 or 90% load at my for my current. So even though it's 100% loaded, it's going to show that you're at 90% current on the input. You haven't changed the load from the previous example, but the power factor has changed. Therefore, the current has changed. Okay. Any questions come in yet, Frank? No? Okay. Then we'll continue. So let's talk about a brief history of the synchronous motors. Okay, the synchronous motor was developed around the 1880s, so it's been around a long time. One of the characteristics of a synchronous motor is we talked about it locking into step with the rotating magnetic field on the stator. So for applications requiring a constant speed, this is a very good motor to use because it doesn't vary with slip. Okay, it also is a more efficient motor. A typical synchronous motor has an efficiency in the area of 94 to 98%. A squirrel cage induction motor to 95%. So they are more efficient. They are more complicated though. The other thing is power factor can be controlled, as we just saw in the V curve, by changing the field, changing the power factor, and we can do some power factor correction, which I'll talk about in a little bit. The other benefit was typically when you see a slow speed motor, a lot in industry are 14 pole all the way through 32 pole motors. Those are off the shelf induction motors. So a synchronous motor, because of the salient pole design, is a better design for those very slow speed motors. Okay. Now, some special considerations though is they do require a starting method, as we just saw. You can use a pony motor to start them, or the amortisseur winding, as we looked at before that. The issue with the amortisseur winding, or it's not really an issue, is that you need a field discharge resistor, you need external circuitry, so it becomes a little more complicated. Also, if you have a brush type motor, you've got the maintenance on the brushes, you have components on the rotor on a brushless system that can fail, and we will see some of that here in some of the later slides. Okay, as far as efficiency go, here I took an example of a 3,000 horsepower, 4160 volt motor, and I assumed an efficiency of about 95.5%. This is the induction motor, the asynchronous. The synchronous motor was a 3,000 horsepower, so same rating, and its efficiency is about 97%. If we calculate all of this out, we come up with a basically the power about 2,300 and roughly 50 kW versus 2295. And if you do an annual cost calculation, we're only saving with the synchronous motor about almost $38,000. So for a smaller motor like this, is it really worth all this for efficiency reasons? There's not a whole lot of savings. However, if we get into the larger motor systems like a 10,000 horsepower and do the same type of calculations, we now come up with about $160,000 in savings. So you tend to see synchronous motors on larger horsepower. You don't see them 100 horsepower, 300 horsepower. Typically, they're several thousand horsepower up through 10, 20, 30,000 horsepower. Okay, and that's based just on efficiency. Like I said, there's other reasons that we use the synchronous motors. Power factor correction was a big one I was involved with. Toshiba, back in the 80s and 90s, we had a brushless synchronous motor. I commissioned a lot of these, and mainly in paper mills, where we would have a mill. In this case here, you see I've got 3 induction motors. There would be a lot more in a paper mill. And each one has a lagging power factor of somewhere around 0.8 lagging. This creates an issue for the power company, because if if a factory has a very bad power factor, they have to put in oversized equipment to handle it. So there's what's called a power factor penalty. If a factory's power factor is too low, they will penalize you. So the customer, the owner of the factory, has to do things to improve the power factor as much as they can. So if we look at these 3 induction motors, and let's say they each are producing about 100 kVAR of lagging power factor, or lagging VARs, kilovars actually. And if we can put a synchronous motor in on the same power line, and we can run it in a leading power factor, it will supply leading VARs that will cancel out the lagging VARs. So you would see these for many applications in a paper mill to do power factor correction. If you didn't do it this way, you would have to add power factor correction caps or static VAR compensators and other type of equipment. But this was a fairly good way to do power factor correction. Now, remember, we're talking here not on a variable speed drive. This was just in a circuit directly online. Okay. Go to the next page here. Okay, we're going to now look at the 3 types of synchronous motors. There's the brush type, there's the DC brushless, and then there's the AC brushless. Okay, the DC brush type, basically, we're going to use DC, we're going to apply it directly to the field coils through a set of brushes. So we would have, on this picture, there would be slip rings, and we'd have brushes riding on it, and the DC would go through some cables and go onto the rotor and be wrapped around all these field coils. Okay, now the problem with that, or not problem, but it requires a field discharge resistor, and it also requires a lot of circuitry. When you look at a motor and you see that it has 100 amps or more of field current, it's typically going to be a brush type motor. Okay, the brushless tend to have very low field current that you hook up to it. So when someone is asking me for a quote for a drive for a synchronous motor, we have to identify what type of motor it is, which one of these 3 types. So that's kind of one way I look at it, is if it's a real high current, then it's probably a brush type motor, but we need to confirm that. The next type is the DC brushless, where we don't have brushes, but we use a rotary transformer, or essentially a generator mounted on the rotor, and we induce the current into the rotor, and then that DC current will feed the field coils. All the circuitry that I talked about, the brush type needed, the DC brushless also needs it, but they mount it somewhere here on the rotor. So it's always spinning. Okay, the next type is the AC brushless, which instead of having DC rotary transformer, you have an AC rotary transformer. And you essentially do the same thing. However, the circuitry on the rotor is slightly different. It has no switching devices, only diodes. Okay, so those are the 3 types. We're going to look at these in detail now, this is a brush type synchronous motor. And remember this photo here, or this picture here that we made. Now, what I did is I put in here, this is the amortisuer winding that I drew in, and that's our starting method, right? So as I apply power and we get a rotating magnetic field, this rotor is going to start to turn because the amortisuer winding. Now, there's a rule that if you've got a wire, you have magnetic flux, and you have relative motion, you're going to get an induced voltage. So these coils here, which are not energized, are going to generate a voltage coming out through your brushes. That voltage can be very high and very dangerous. It can exceed 1,000 volts. So what we have to do is take a low resistance, attach it to it. This is called a field discharge resistor, and that will keep the voltage at a low level. It also acts to increase the starting torque. It acts kind of as the amortisuer winding does. It gives you more starting torque. So any brush type, you're going to have this resistor when you're starting it across the line. Okay, and you have to have an exciter panel, which has a whole lot of other circuitry that we're going to look at. Okay, here is a typical exciter panel with the same motor. Okay, as we apply power to the stator, we induce the fields into the rotor. We start to turn, and you'll notice out here in the exciter, we have that field discharge resistor. It also has a couple contacts marked FC. This is the field contactor. It's a large DC contactor, and it has a normally closed and a normally open. We also have a three-phase bridge here made up of SCR so that we can control how much DC is produced. So we're going to see here, there we go. As this starts to rotate, our current flow is going to be down through the field discharge resistor. So we're going to have this current flowing. We're going to keep the voltage at a decent level. We also have a relay here marked FR, frequency detect relay. And remember, as this is coming up, we have slip, right? We're not synchronized yet. And the faster the rotor turns, the less the slip. So the frequency of this current flow is proportional to the slip of the motor. What this relay is, FR here, is going to do is monitor the frequency. And when we're at about 3% slip, it's going to activate. It's going to apply the field to the rotor, and it's going to turn off the field discharge resistor. And we can see that in this example where it closed this, put power to the field, and it opened the field discharge resistor because we now want it out of the circuit because it's low resistance. It's not rated to be in there continuously. So this is all the circuit that you need to supply with this synchronous motor. Okay. The contacts here are a closed transition, meaning that this top one here, the FCA, closes before the FCB opens, because you don't want to have that open transition or you could get a high voltage generated on the field discharge resistor. Okay, let's look at a DC brushless. If you look at the circuit that I'm highlighting right here, this is the exact same circuit that we just saw in the brush type, except it is now all mounted on the rotor. how we get power into this circuitry is we have a DC set of coils here that we apply power to. Then we have the secondary windings on here. So as it starts to spin, we're going to induce a voltage in that then at the appropriate time, we can switch it on. So here's how it works. So we put the power in to the DC coil. Now, remember, at this instant, we're not turning, the rotor is not spinning, so we do not get an induced voltage. This motor has no AC applied to it, so it's just sitting here with DC on these coils, and that's the first step. Once we apply our stator current and we start to rotate using the amortisseur winding, we're going to start generating a voltage in this coil. So that's going to feed up here, and you'll notice we have SCRs. So we're not actually going to turn on the DC coils here. Right now, it's generating a voltage, which is going through our field discharge resistor, just like we did in the brush type circuit. This is a control box that's actually monitoring the slip frequency of this current, and at the appropriate 3% slip, it's going to fire these SCRs, which we can see over in this example. It'll fire these SCRs, and it's going to apply field voltage to the field coils. And it's going to then turn off the field discharge resistor. So the same circuitry as the brush type. However, this section's all mounted on the rotor. Okay, let's talk about an AC brushless. This is an AC brushless, and you'll notice it has AC coils on the stationary part. And here's the secondary part, which is on the rotor. And you'll notice the difference here that it only has diodes, so it has no switching device. It does not have SCRs, does not have a field discharge resistor. It does not have the control relay. So this type of system is not going to be able to be self-started. So this AC brushless is what you'll typically find on a variable frequency drive, because we're going to start it differently. We're going to see that shortly. Okay, when we look at this, when we put power on to the field, we generate magnetic field, but because this is AC and not DC, we do get a voltage generated. So immediately we can energize the field coil, even though we haven't applied main power to the motor. And that's going to become very important when we're working with a variable speed drive. Okay, let's talk about how we operate on a VFD. Okay, just to refresh your memory, our VFD, you have three-phase AC coming in. We're going to convert it to DC, and then we're going to output a 0 to 60 hertz, 0 to 100% voltage. And that's going to have a volts per hertz ratio. So at half speed, you'll have half voltage, and so on. Okay. So let's see what happens here. The requirement for running on a variable frequency drive is we're going to apply the field at start. Now, remember in the across the line examples, we had to start it and get it up to speed. Then we applied the field using our frequency detection relay. In a VFD, what we're going to do is we're going to apply the field first, and then we're going to start the drive. And the VFD is going to control the field current. Whereas before, you would have controlled the field current either from your PLC or from a speed pop, or say a rheostat, or some way you could control it. The motor will be controlled at unity power factor, and the VFD will provide our pullout and field loss protections. So let's look at one. So this is where it is very important in this section here. Remember the brush type motor, the first one we looked at? So the external field controls could be customized for a VFD. So instead of having all that circuitry, we can just have a rectifier and a switch to apply the field directly. Remember, that was one of our requirements for the VFD, is that we can apply the field before starting the drive. There's no synchronizing controller required, no field discharge resistor. So can we use it on a VFD? The answer is yes. This type of motor, a brush type synchronous motor, we can, that shouldn't say, it's a brush type, that shouldn't say brushless there. Sorry, that's my mistake. The second one, a DC brushless, if you remember, when we went through it, we said the DC is applied here, but since it's not turning, we can't get power to the field coil. We've got all this circuitry here that's going to prevent us from doing that. So we're not able to use this one on a VFD. So I get requests all the time that say, I have a brushless synchronous motor. Can you supply me a drive? Well, that depends. Is it a DC brushless or is it an AC brushless? There's an important distinction there. So the AC brushless, here's the circuitry. Remember, it doesn't have all this circuitry here in it. So we can put AC here. We immediately get AC, goes through the diodes. So we power up the field immediately. So yes, we can do AC brushless or a brush type synchronous motor, but we cannot do a DC brushless. So if you're sending in a request, you have a synchronous motor, we need to identify exactly what type of motor you have. Okay, this is how our circuit would look. Over here on the right, this is a VFD. Here's the main power coming to the stator. This is your exciter panel over here. So this essentially is going to put out, this is for a brush type motor, so it's got to be DC that we're going to put out. And it's variable because we have SCRs, so we can control it. The field will come over through the brushes and into the rotor. So what's going to happen is we're going to apply the field first. So we'll have a contact here that says start. It comes over and tells the field to turn on. We're going to put field voltage onto the coils. Then we're going to come and we're going to start the drive and apply the voltage from the VFD to the stator. And we're going to start to increase the speed. So when we start off, we're going to already be synchronized with the magnetic field. Remember, previously we looked at you start it and bring it up to speed and then synchronize. Here on a drive, we're going to synchronize it. Then we're going to apply the voltage to the stator. So that's going to be different. It's going to start synchronized and it's going to stay synchronized throughout its speed range. We have to control and run at no more than unity power factor. So the drive will output a 4 to 20 milliamp to the exciter, which will vary the field current. Now, if you go back to those V curves, you could figure out how much field current I need for a given load. to give me a unity power factor. The algorithm in the VFD already will do that. Then we will also supply things like the voltage and current over here so that the exciter knows what power factor it has. And if we get a fault in the exciter, it will tell the drive to shut down. So there's a few signals going back and forth, but that's essentially how we're going to do it with the drive. This is a brush type. This is the AC brushless. Remember, DC brushless we can't do. So here, once again, we're going to this time put out 0 to 300 AC. We're going to energize the field coils. Then we're going to turn on the drive, which is going to synchronize and take off. Now, one of the things about this is we need to put the proper phases on this on the stator, depending on how the rotor is configured. So what this drive has an algorithm that will do is detect rotor position. The way we do that is turn on the field at first with a pulse on and then off. We're going to measure it. We're going to figure out what phase relationship we have, and then we'll output the proper phase relationship to the actual motor windings. And this is what it's going to look like. So our field initially, we're going to apply a pulse of field current. This is probably about a half a second or less. We're going to detect the proper phase relationship. Then we're going to start increasing the output frequency of the drive. And it's going to control the DC so that it maintains that unity power factor as it comes up into speed. Okay, so it's very important that we do that, and that's all built into the synchronizing software. Okay, there are protections that need to be. Some of the exciters will have this protection in it, the pull-out relay and the field loss relay. Because if you lose your field and pull out of sync, it can damage the motor. So anytime that happens, you want to shut down. So this can be provided within the VFD itself. It monitors the power factor. If the power factor goes lagging, which means it pulled out of sync, then it's going to trip offline. Also, if it loses field, you can program it to trip. So you don't need all that extra stuff built into the exciter. Okay, one of the considerations that we have to make here is when we're sizing it is if we have long leads or the leads to the field are fairly high resistant, this pulse may not be large enough. So when we're sizing the exciter, we'll typically size it for 125% of the normal field voltage rating. That makes sure that we do have enough field voltage to get this pulse so that we can read rotor position. Okay. Let's talk about, is there any questions that come in? Yeah, okay. So special configurations that I want to kind of cover here is starting duty only. This is an application that we've done numerous times in which they may, in this case, have a 10,000 horsepower motor. And in this case, it's a natural gas compressor. That compressor is starting unloaded, and it only requires maybe 7,000 horsepower to turn it. So what we do is start it. We size it for a 7,000 horsepower VFD. We start the motor and bring it up to speed. just like we were talking about a while ago. We apply the field, it's synchronized, we bring it up to speed, and we do use what's called a sync bypass circuit to transfer it across the line. Once it's across the line, now they can load it down to the full 10,000 horsepower. And they can also control their power factor, because what we'll do is give control of this back over to the customer. Because initially we're controlling it with the drive to regulate it to unity. But once it's on bypass here, the customer can take control and run it at 0.8 leading and can do some power factor correction. And we've done this on numerous occasions with this type of situation. Okay. We also have had run into this situation where the customer has a 13.8 kV motor. Well, we can take our 4160 volt drive and use a step-up transformer to run a 13.8 motor. The problem is, as we were discussing, is we need to detect rotor position. To do that, we would pulse the field current. The problem is that pulse can't get through this sine wave filter and transformer. So what we have to do is bypass all of that, start this motor on 4160, get it synchronized, and then switch out the 4160 and go back to the 13.8 and continue. So that is something that we can do. We've got a number of applications that we did that. Okay, and this was a situation where a customer inquired about, I want a bypass with my drive, and I want to be able, if the drive goes down, can I start the synchronous motor? It was a brush type across the line. Well, yes, we can do that. The thing we have to consider here is we have to set the field circuit up for two different situations. Remember, on the drive, we are going to apply the field directly with no control. And then we will control the field current with the drive. But if it's on bypass, which would be across the line, we have to have the field discharge resistor, the FR relay, the field contactor. So we would have to put a relay that you would select between VFD mode and bypass mode. So that is also something that we can do. Looking at the AC brushless system, I should say brushless type there. I'm sorry, I have another typo there. Remember, we put our three-phase voltage here, AC. We get our field immediately. So the question the customer asked me was, how do I use an AC brushless? I want bypass. I want to be all started on bypass. And as you can see, we have no way of holding off until it's up to and sensing when it's at 97% speed to do it. So basically, we can't do the bypass on the AC brushless. Okay, so that concludes what I had to cover. Is there any questions that you have about any of this?
So in comparison to the VFD for the asynchronous motor, these VFDs are more expensive. Yes, to set a circuitry.
Well, the VFD is really the same. There's no additional expense. The AC exciter or DC exciter is a standalone unit that also adds cost to it. The average cost of an exciter, is maybe 60, 70,000. They're not all that expensive. So, but it is more expensive because you do have to have that excitation source. And it's going to depend on if it's a DC brush type where you have to have the additional field discharge resistor and all the other things with it? Or is it just a AC exciter, which is nothing more than for the AC brushless would be a thyristor package that can be controlled. So yes, they do add cost, but it's not really all that much in comparison to the cost of, let's say, a 5,000 or 6,000 horsepower drive. Okay, any other questions here? Okay, then that concludes my presentation.